All right, you can unmute your mics and join the discussion. So, yeah, the quick discussion beforehand again, Pete and I agreed that we should just do the next two parts, which will leave three parts for the next session. Otherwise, unfortunately, the next part six goes on for half an hour, which would take us into just over an hour this evening. But unfortunately, it also takes us part 6, 7, and 8 together form about an hour for next session. So I don't know. We're going to have to see how we deal with that. Yeah. Does anybody want to open the discussion on this lot? It's basically about quantum entanglement, I think, the section. Does anybody understand quantum entanglement? Does anybody understand what this guy was trying to explain?
Not at all.
I don't think he explained very well. He didn't. I mean, it's probably too much. It would have taken too long to go into the detail of those experiments. But I don't understand exactly what were they measuring. When they were measuring from two different stars, what were they comparing to what, and what were the results exactly? I don't understand it. So it's a bit of a. I mean, I get the basic sort of quantum entanglement concept, even though it boggles my mind, but I don't see where they were looking for it in those experiments, how they found it and how they didn't, or what they didn't find, or what they proved exactly. What were the exact mechanics of how they handled the experiments? I think that's a bit of a mystery. Does anybody have any idea of what happened there?
No, I really don't know what to say here, Derek. I've read about this several times before, and it has me completely baffled. I'm not sure I get the idea of entanglement, but I suppose I'm thinking in classical terms. If I had like two coins, one was heads, the other was tails, I didn't know which was which, and I separated them by 50 kilometers, I could say that each of them has got a probability of 50-50, but when I look at one, the other must automatically be the opposite. Does that mean to say they're entangled? I don't know. I don't get it.
So that is what they think, the theory of entanglement. And I think that this is what they did find in experiments. They literally did this on opposite ends of the Earth. They did somehow separate photons, which were entangled, and then they detected one as being whatever orientation, and then they detected the other as being the opposite orientation every time. So there was definite entanglement. So yeah,
Thinking about
instantaneous. So to me, it's almost like the three spatial dimensions. The entanglement is in a different dimension to the three spatial dimensions. So the entanglement exists throughout the universe between two. In other words, the three spatial dimensions just fall away. It's as if they're in the same spot and not being separated.
Well, thinking about what's been said in previous videos, as far as light is concerned, there is no distance from one side of the universe to the other. It's zero. So therefore, shouldn't we expect this spooky action at a distance? Because as far as light's concerned, there is no difference. There is no distance.
Yeah, so I think that comes from the concept of time and the speed limit of light. Because light has no mass, or photons have no mass, and they travel at the speed of light. Because they travel at this time is slowed down to zero. As you go faster, time slows down more and more until you get to the speed of light. Then it's at zero. Then there is no time. So even
and there's no
us,
distance either.
Even though for us the time of a particle from the origin of the universe takes 13.8 billion years to reach us, for the light particle it's taken zero time. So from that point of view, it's like it is at the same point. It hasn't moved although it has moved. You see what I mean? So it's like, because time falls away, it's almost like the three spatial dimensions fall away for the light.
Yeah, that's the point I was trying to make, I think. So this idea of
Yeah.
entanglement, is it that surprising? Since to light there is no distance between the two. You measure one particle, it's in one orientation. The other, it takes no time at all to change the other. So maybe I'm
Okay,
missing something.
that sort of explains the entanglement of two particles which have no mass. But two particles which have mass, can they also be entangled?
I'll leave that for someone else to answer, Derek.
So yeah, it's a bit of a
This is where we need. This is where we need Pierre. Where's Pierre when you need him?
yeah. So yeah, look, I think they guys like Feynman said, look, there is no solid particles, or no, there is only there are only waves. Everything is made of waves.
Mm.
And I
No,
think
get
one has
that.
got to understand that properly. I don't know if anybody really understands that properly. If everything is waves, why do particles feel solid? So if you explain that properly, what
The
is the
trouble is this.
mechanism that leads to that? The appearance of solidity. A baryonic, I think it's called a baryonic particle. So, a proton, you can't have one proton just going through another proton. They can't occupy the same space.
As soon
And
as you
although
make
everything is
something,
waves, why is that true? If everything is waves, why can't things just go through each other?
as soon as you make something solid, it begs a question. Then, what is it made of? Can you chop it in half? So, so really, waves is
Yeah.
the only way to go.
So in my mind, I've got my concept of how it is possible. Um, I think there's got to be some basic property like the maximum speed of an electromagnetic wave. It's just a fact of the universe. It's been measured, but nobody understands why it is that a particular value, why the speed of light is 299 million, whatever, meters per second.
Mm.
It's just a fact of reality. But I think, if a particle, even like a quark, is a wave which has reached some sort of harmonic point where it's some sort of a stable thing which appears to be a part. Maybe you can't. Maybe something within that wave has reached the limit of the speed of light, for example, and you can't then add more to it because it's reached the limit that there is.
Mm.
And to me, that is almost what can prevent one apparently solid particle from moving into the space of another one.
Mm.
The other thing is, of course, electrostatic repulsion. If two things have a charge and they have the same charge, then it simply would. I mean, that's a standard explanation I've seen for why you can't fall through your chair. It's because there are electrostatic forces between the electrons at the edge of every atom repulsing each other. So I don't know.
There's also probably the element of probability there because you would have to have the probability that everything's lined up where you could pass from one side to the other.
Somebody's going to crack that one day and figure it out, like they do in the science fiction where somebody tells their brain to vibrate their body to a certain frequency and they walk through a wall.
Yeah, the entanglement thing is a bit that baffles me. I can understand the concept of like particle wave duality, if you like. I think of it as like an analogy, like a bowl of custard. If you put your hand into a bowl of custard, you can move your hand in and out quite freely. But if you try to like smack it, I mean, you can walk on custard. I believe, if you walk fast enough. And it's the same sort of principle. It feels almost as if there is like stepping stones there.
Yeah, there are, what is there? There are some other,
I think
it's called, I
cornstarch
forget
is
what the
another one
term is.
like that.
There's a term, yeah, where you give something a rapid tap and it almost solidifies for that instant and
I
then
think
goes
it's a
back to it.
thixotropic.
Yeah.
Thixotropic, yeah.
Okay.
Thixotropic. Mm.
Yeah. That has been explained by somebody that figured it out, but I'm not sure what the explanation is. So yeah, I think the wave particle duality. You see, what I was trying to say is, there's something in the wave component of a, well, let's just say a photon. Could be the same for an electron. If there's something which has reached its maximum, it is a wave. But there's something which cannot, and that's what interacts with other things to make it seem as if it's behaving like a particle. But it is still a wave.
Yeah. Fascinating.
Yeah.
Derek, it's Gert Steenkamp, Johannes Steenkamp speaking. I must say I find this entanglement story incomprehensible. To be very honest, I think I'm still of the same opinion as Einstein that someday we will find out that there's a simpler explanation. I'm really skeptical. I find it interesting to listen to all these experiments and things, and I guess it's hard to argue with it. But I'm sorry, my mind cannot get around these things. So for me, it's just interesting, and I don't want to understand it. I cannot understand it. So this is where I am.
Yeah, look, I think that there are sort of conclusions which are based on observation and based on logic that this is how it must work to get those effects. But I think there is a definite lack, there is a gap in understanding exactly what the mechanism is which produces this effect. So, I think when some genius comes up with the answer of, what is a mechanism which causes this, which causes spooky action at a distance, then I think we will have the answer. And I think everything in the universe, I think, can be explained logically, but you've got to have the knowledge of the sort of in between steps. And
I think
it's going to
that's my
take a
problem.
genius to find out what those are.
I think that's my problem. You said that everything can be explained logically. I think we are missing some pieces of the puzzle.
We're definitely missing some pieces.
Yeah, therefore, to mere mortals like me, it doesn't seem logical. So maybe one day, as you say, a genius will find those missing pieces, and then it all makes sense. So we just have to be patient.
If it was a head scratcher for Einstein, then I feel a bit better about it because it's a head scratcher.
I just want to make another comment. What I also find strange is all these new particles, up and downs and quarks and muons and things that they are discovering. It is just mind-boggling. Huh? It seems like every time when they smash certain particles in an accelerator, then they discover another particle. That also is not logical. Doesn't make sense to me. Just an observation.
Yeah, look, they had the theory of what they should be, and then they started getting pretty good at it, and they started predicting particles, and then they started finding them. And I mean, as we know, the last one was the Higgs particle, which they actually found. But I mean, what they found was, what they see in their detectors and how they calculated that was the particle they saw. It's a little bit of a mystery to me, and it's a bit of a probability almost exercise as well. But yeah, so again, if you come back to the fact that everything is wave, if you just remember that, if you're smashing stuff made up of certain waves which have certain properties, which appear to be a solid, and you smash it with enough energy into another thing, then those waves can separate and can lose some of their stuff, and that's when you start seeing the new particles. You get new bits of the one particle combining with other bits of another particle and forming a new particle. So it's what is a wave? If you come back to the concept of a simple guitar string, if you have a guitar string which is sort of tied down at its ends to something and you just pluck it in the middle, then it makes a wave which is a unit. It's the wave which is over the whole length of that particular piece of string. It's what is it? What is the mathematical term? It's integer. It's not a fraction of the length of the thing. And if you hold your finger in the exact middle of the string, then pluck it sort of a quarter of the way along, you'll get two waves, which are exactly, each wave is half the wavelength of the total length of the string. So things work in integer fractions and so on, as far as waves are concerned. And I think that's what's happening at the subatomic level. You've got some basic dimension in the universe, which is the ultimate dimension, which everything is a multiple of. And that to me has got to be something. It's got to be something like that. And that can explain when things start, interacting as multiples of the integer lengths. When you start getting quantization. And you get different, what appear to be particles with different properties. It's just different harmonics of different frequencies within the waves. So let's hope that in our lifetime some genius is going to explain it. Otherwise we're going to end up like Einstein and going through our lives without knowing the answers. But anyway,
I fear one day when I've understood it, they're going to change the goalposts and come up with something else.
Yeah, they've come up with a better problem.
Yeah.
Oh, well, life would be boring if we understood everything perfectly, wouldn't it?
Absolutely. Anyway, it's a very interesting topic. I'm looking forward to the next bit. I think I'll have to read the transcript before I listen to the video. It does help.
Yeah. All right. Anybody else? I think we're pretty much on the same page here. And I don't think we need to feel bad that we don't understand it exactly. I think nobody does.
Thank you, Derek.
Oh, that's consolation. Thank you very much.
Yeah. All right, let's have a look. Who's attending? We've still got 7 participants. I think Jenny Morris has dropped out. 1 or 2 others. All right. Would you like to call it a day there and we'll meet next time?
Yes, I think it's time to enter this entanglement. Okay, thank you very much, everybody.
Let's untangle the entanglement next time.
Thank you. Bye-bye.
We'll see you then. All right.
Thanks,
Cheers.
Derek.
Have a good supper.
Thank you.
Yeah.
Bye.
Yeah. Good night.